Okay. Uh, you take it away. You can share your screen, or if you need to, I'll unshare. I'm not sure if it's necessary or not.
Yes, just give me one moment.
Sure.
I think you do need to unshare your screen.
Okay. Got it. Done.
Okay, can everyone see it?
Yeah.
Okay.
Perfect. So, our project is simulating Lincoln Tunnel, and our research question was, did New York's 25 congestion pricing policy help reduce traffic delays, especially at Lincoln Tunnel? And me, Matthew, and Taylor made the project. Next slide, please. So, as you can think that why Lincoln Tunnel? Why just a single tunnel, right? So the reason was it is the most heavily congested choke point in the New York City area. And there were several news reports highlighting that. Now, all of these news reports are pre-2020, but they all make the point clear that Lincoln Tunnel was very congested. Like one of the reports even saying the annual delay causes travelers more than 3.4 million hours, imposing a financial cost of more than $87 million annually. And personally, like traveling from Hoboken to New York City in 2024, like in the last semester, right, I could be held up in jams for over an hour. It was very easy, especially on Fridays. And now it's consistent, below 30 minutes always. No matter what time it is, no matter what it is, I get that timing. So next slide, please. And now Matt will introduce why congestion pricing is, and then Taylor will follow on to our model, describe its assumptions, and then I will come back on the results.
Yeah, thanks, Tamme. Like you said, I think it's important, and we think it's important to just talk about what congestion pricing is and its history before we can even get into our model and our simulation. So that being said, congestion pricing is a policy tool designed to reduce the number of vehicles in high traffic urban zones, especially during peak hours. The idea is very simple. Charge drivers a fee to enter these areas and, in turn, encourage alternative transportation methods like commuter rails, buses, and subways. The main goals are threefold: reduce gridlock, cut down on greenhouse gas emissions, and then create safer, more breathable cities. Ideally, fewer cars on the road mean shorter commutes, cleaner air, and safer streets for everyone. Next slide. In response to decades of worsening traffic, New York City launched its congestion pricing program on January 5th of 2025. The system applies a flat fee, which is $9 for most vehicles with an easy pass, once per day to enter Manhattan's congestion relief zone, which covers areas south of 60th Street. The charge applies during peak hours on weekdays, which are, 5 a.m. to 9 p.m. on weekdays and then 9 a.m. to 9 p.m. on weekends. The initial impact was very significant. Just in the first week, there's a 7.5% decrease in the number of vehicles entering the zone, which comes out to about 43,000 fewer cars compared to the same week in 2024. The reduction alone shows how quickly the policy started influencing driver behavior. Next slide. So, so New York City is not the first to experiment with congestion pricing. Cities like London and Stockholm have successfully implemented similar programs and can offer helpful comparisons. In London, traffic dropped significantly, as you can see in the chart, after the congestion charge was introduced in 2003. Stockholm saw similar reductions in congestion and reported improved air quality and public support over time. The international case studies show that while there may be resistance at the beginning, the long-term benefits of congestion pricing are well documented and widely recognized. So next slide. So Jeremy Hinsdale of the Columbia Climate School has compiled early data from the from New York City's program, and the results, to say the least, are very promising. So first, there was a major drop in vehicle entries, comes out to over 1 million fewer cars in Manhattan's core in just the first month, and commute times through key tunnels, including the Lincoln Tunnel, dropped as much as 48%. Subway ridership also rose by 7% on the weekdays, and weekend express bus ridership increased by 20%. Financially, the program is set to fund a $15 billion in MTA upgrades, including new electric buses and long overdue accessibility improvements. Less traffic also opens up possibilities for redesigning urban space, such as Times Square's transformation into a pedestrian plaza. And finally, there are measurable health and safety benefits. Crashes in the toll zone dropped by more than 50% in the first few weeks. Cleaner air and quieter streets are expected to improve public health outcomes over time. Next slide. Thank you. And despite its benefits, the policy is not without criticism, especially when it comes to equity. Critics point out that flat fees can place a disproportionate burden on low-income drivers who may or may not have access to public transit alternatives. Some outer borough neighborhoods, such as parts of the Bronx or Queens, have limited transportation infrastructure, meaning residents rely on driving and are hit hardest by these tolls. There is also a concern about geographic fairness. Residents inside the congestion zone often avoid the toll, but still reap the benefits of the reduced traffic. In addition, quieter, cleaner neighborhoods may see rising property values, potentially accelerating gentrification and displacement of longtime residents. And finally, the planning process has been criticized for not including enough voices from these impacted communities. Equity-focused solutions like transit discounts, exemptions, or reinvestment in underserved areas will be essential to ensure the policy benefits all New Yorkers fairly. And next, Tyler will talk about our model.
Sorry. So here we just have just like the basic links about where we received a lot of the data from. So a lot of the data comes from either the New York, Jersey Port Authority, the New York City DOT, or even the state government. The only problem, the difficulty with working with data from three sources is that the way they record data can be different for each organization. So it and a lot of the data just does come up with just though inconsistencies with how they record what times they record it or the time periods they have. So how we worked with it was we just first took into account the real world counts from 2024 and 2015. Then we just created simple 24-hour traffic curves trying to figure out how the on average traffic exists within the Lincoln Tunnel. And we try to create a times table for approximately 10 minutes over six different slices of the day and populate monthly totals and times tables. The data we did receive, we tried to get in our model, we concretely coded the data so it rather than extracting it from an Excel file, we increase the speed. And we tried to break it down between different cars or trucks based on typically when trucks or automobiles run through the tunnel. So we have to create a bunch of assumptions for our model, as many of them, as just the data just includes, it just has so many data points. So first, regarding the lane capacity, we assume that each tunnel can serve approximately 250 vehicles within a 10-minute window, which translates to about 1,500 vehicles per hour. The capacity is considered fixed for all different types of vehicles, as it would have been pretty difficult to take into account variations of size between trucks or buses and different automobiles. So, in another thing would be the number of inbound lanes available can vary for the Lincoln Tunnel, as there are on weekdays there are 3 lanes operating for the peak morning commute hours, which is 5 a.m. to 12 p.m., then reduces to 2 lanes or 2 tunnels for 8 p.m. and 1 lane overnight. For the weekends, we assume that 2 lanes are open for 6 a.m. to 8 p.m. to balance daytime traffic, again with 1 lane overnight to allow for bidirectional use if needed. A critical factor in speed versus occupancy would be that we set the free flow speed about 30 miles per hour, meaning a vehicle could ideally pass the 1.5-mile tunnel stretch in about 3 minutes. However, the tunnel gets more crowded and often as occupancy increases, speed is reduced. For example, if the tunnel is up 30% in occupancy, vehicles can maintain 100% of the speed. If occupancy jumps over 85%, speed drops down 25% of the free flow speed. So, or about 7.5 miles per hour. As we model the speeds and reductions in a stepwise fashion based on specific occupancy thresholds. Regarding tolling prices, we in EasyPass Share, our model assumes that 85% of the vehicles use EasyPass and pay a toll of $13.75, while remaining vehicles pay cash or without EasyPass paying $16. This pricing was fixed for the base toll. For the year of 2025, we introduced CRZ surcharge of $9, which was applied to every vehicle in addition to their base toll. So to handle these situations where demand capacity exceeds demand exceeds capacity, we implemented a unique model that wait time calculate based on the number of vehicles in the queue and the tunnel capacity, assuming vehicles arrive steadily over a 10-minute block. So that's how we have our so here we how our model would typically flow is we would load the data for 2024 previously before congestion pricing, and after we implemented congestion pricing for 2025. In our model, then we load the data and it assigns lane capacities by the time of the day and from there we simulate the traffic flow for each time block. And then we would compute wait times and travel times. The wait time would just be fully computed based on if there is a higher capacity at the time, or if the tunnel volume capacity is at max or below its maximum capacity. And we would calculate the revenue, which is just a simple calculation based on the EasyPass percentage and the cash paying users plus the congestion pricing surcharge. So there's a few limitations with our model, which would just be that we can't really have fully randomness based on if there's crashes or weather or ideal conditions based on we can't also adjust for if like NJ Transit, because we're coming from New Jersey to New York, is shut down, or if more commuters are coming into work via cars just because public transportation is not working sufficient. And the traffic curve are assumptions from almost 10 years ago. And we have a static mix of vehicles to trucks or buses. And we don't really have, as I said, no behavioral response based on individual drivers' reaction to tolls and overall volume reductions. So Antonio would take over with our results.
So, like I said before, and the graphs can suggest that the average tunnel time, the congestion pricing led to a substantial reduction in the travel times, right? And if we look at the blue line in the first graph, we can see that it goes up to 50 minutes, right? Around the time which is between 3 p.m. and around 8 p.m., right? So the congestion was very large and speeds were reduced by a whole margin. And we are using the same model for both the data sets, both 2024 synthetic data set and 2025 real data set. And in the real data set, we can clearly see that the average travel time has reduced for across all hours of the day. Now, this is the average of the first 4 months that we had the data for, the real data for 2025, and 2024 was the whole year. So, and the distribution of individual travel times, right? So the mean travel time for a vehicle across the whole day was less than around 4 to 5 minutes, right? And there were a few outliers. And in 2024, the mean could be anywhere. The mean was around 5, 6, or 7 minutes, slightly higher than the mean from slightly low, higher than the mean from 2025. And the 75th and 25th percentiles are 75th percentile is much higher. And as we can also see, since the data set for 2024 was a synthetic data set that we created, the number of outliers come in a very straight line. It's almost as if it's a straight line, which is which is, what one of our assumptions is clearly stating here. Next slide, please. And if we look at the throughput data, so the average queue length dropped dramatically in 2025 following the implementation of congestion pricing. And the vehicles in queue decreased from over 8,000 at certain times of the day, at certain days, to less than 5,000, which is also the biggest outlier that we have. And the hourly throughputs also decreased by a very huge margin, which is evident in the second graph. So the queue length dropped from sustained peaks of over 8,000 vehicles in 2024 to near zero levels in 2025. And the hourly throughput also decreased, which said the reduction was relatively modest, suggesting that the vehicle flow remained stable despite the surcharge, while the system efficiency improved. Next slide, please. So if we look at the revenue data, right, before 2025, only toll was applied, but post 2025, both toll and a surcharge was applied. And due to the surcharge, our revenues, instead of decreasing, increased, even though the total vehicles passing through the tunnel decreased. So and in the initial months, the total revenue exceeded $30 billion, which was not the case for any months within 2024. And it was nearly 40% higher than the same months in 2024, with the surcharge alone contributing over $10 billion. Next slide, please. So did it really make a difference? Yes, I think so. So the average tunnel time dropped from over 40 minutes to under 15 minutes during peak hours after congestion pricing was implemented. And afternoon peak travel times averaged 40 plus minutes, while many vehicles facing extreme delays. Now, post 2025, the travel time stabilized to under 15 minutes with tighter and more predictable distributions, which is something that I felt personally while traveling through the tunnel also. Now, queue lengths fell from sustained peaks of above 8,000 vehicles to near zero, and the revenue increased 40% due to the $9 surcharge. And there were faster commutes without significantly reducing the throughput. And the policy is also in line with New York City's climate, public health, and transit goals. And as I said, my personal commute dropped, and our simulation confirmed this real world change that I personally could see. Next slide, please. So to conclude, the 2025 congestion pricing did improve the traffic flow through the tunnel, and the travel times dropped, the queue lengths fell, and the revenue increased. And these results align with the real world reports of reduced commute times and increased transit use. And now I would open the floor to some questions.
So first of all, thank you very much. It was very interesting. Anybody want to make a comment or a question? Okay, what? Go ahead.
So in the beginning, you talked about the different data sources that you pulled your data from. Can you talk about that a bit more? How different were they, and
Sure.
how much trouble did you have with that?
Sure. So you must have realized that we used 2015 data sets for the granular data because we could only find 2015 data sets with the granular data. And we had numbers for totals for both 2015 and 2024. So what we really did was we sketched the traffic curves for 2015 and then modeled it onto 2024 and made sure that the totals for both the years, in 2015, it was around 1.1 million vehicles passing through. And in 2024, it was around 1.4 million vehicles passing through. So we increased the amount of vehicles that were passing through the hour. Now, our traffic curves were by the hour. So we had to bring it back to the 10-minute levels, which our 2025 data set was in, because 2025 data set was really fine. So what we did was we took the 1 hour blocks and slashed it by 6, and throughout the hour, same number of vehicles come in. And throughout those 10-minute blocks, it takes the same, same distribution as it would for the 2025 real data set. And this was also, I believe, could be seen in the travel time, travel time graphs, which, the 2025 data set had really many outliers with some going above 100 minutes, while as the 2024 data set had outliers, but they were really flat. So, yes.
Okay,
you.
thank you. Anybody else? Okay, I will stop the recording. Worry about it later.